We can also use integrals to find areas between curves. For example, if I want to find the area between these two functions, I would start by drawing a picture. So I have the function y equals x squared minus 4x. That is a parabola that opens up. And then I have the line y equals x, goes through the origin. So the problem says find the area between the curves. So in green, this is the area I'm trying to find. If I want to find the area between two curves, I have to figure out where they cross. Those intersection points are going to be my bounds of integration. To figure out where they cross, I'm going to set these two functions equal to each other. I'll set one side equal to 0 by subtracting the x. I can factor an x out. And I have two solutions, x equals 0 and x equals 5. So that's telling me that these two functions, these two curves, intersect at 0 and 5. And so if I want to find the area between them, I'm going to integrate from 0 to 5. And what I'm going to integrate is always going to be the top curve, which in this case is the x, minus the bottom curve, which is the x squared minus 4x. So you always integrate top minus bottom. Before I do the integration, I might as well combine like terms. And so the problem that I'm trying to solve is from 0 to 5, 5x minus x squared dx. My antiderivative is 5x squared over 2 minus x cubed over 3. And I'll be evaluating at 0 to 5. So I plug in the 5, I plug in the 0, and I subtract. And I got approximately 20.83. That would be the area between those curves. In addition to area, definite integrals also give you total values, total accumulation. They're really adding things up. You're adding y values together. So if you're asked to find a total value or a total accumulation, that is asking you to integrate. In example 6, it says the rate at which a substance grows, and this r prime is also a clue. They're giving me a derivative. They're telling me x is time in days. What is the total growth, the total accumulation during the first 3.5 days? So what they're asking me to do here is to integrate from day 0 to day 3.5. And I am going to integrate that rate of change, 150 e to the 0.2x. So again, that total accumulation is what's telling me to integrate. So to integrate, let's see, I would get 150, the constant, times 1 over 0.2 e to the 0.2x. That's the same as 750 e to the 0.2x. And now I'm going to have to plug in my bounds of integration. I'm going to plug in the 3.5. And I'm going to plug in the 0. I put this into my calculator, and I ended up getting approximately 2.688. They didn't really give us any units, so I don't know what that is telling us, maybe grams, pounds, something like that. Finally, I want to show you a specific business application of integration. And this application applies to demand and supply curves. And so what I have shown right here in this graph is in red, I have a supply curve. And in blue, I have a demand curve. On the axes is Q, which stands for quantity, the number of items. And the y-axis is P, or price per item. So notice the demand curve is going down. Basically, the lower the price, the higher the demand, whereas the supply curve is going in the other direction. The higher the price, the more the suppliers are willing to make. The place where your demand and supply curve meet, this intersection point, is your equilibrium point. And we're going to give this point coordinates Q naught, P naught. That's our equilibrium point. Now, the concept of a consumer surplus is basically describing the idea that if you set the price at the equilibrium price, you miss out on the fact that some of the consumers were willing to pay a little bit more for that item. And you could think of that as some kind of lost revenue, money that you weren't able to take advantage of. And the region of this particular image that is the consumer surplus is what I have shaded in red. This area in red indicates basically all the items that people would have purchased for higher prices and the total money that could have been realized. And so finding this area is what we call the consumer surplus. And I have a formula right here for consumer surplus that says basically this area you integrate from 0 to your equilibrium quantity. The top curve is your demand function, and the bottom is your equilibrium price. Now, there's also something called the consumer surplus, there's also something called the producer surplus, and that's this area right here. And this region is describing the fact that some of our suppliers were willing to make this item at a lower price. To find this area, I have got another formula for you that's very similar. All right, there is my producer surplus. So this time the top curve is the price and the bottom curve is the supply, top minus bottom, and we integrate from 0 to the equilibrium quantity. All right, so let's do an example. We are given a demand function and a supply function. The demand and the supply, the D and the Q, are actually prices, and the Q is items. To find the equilibrium price and quantity, we have to figure out when does our demand function equal our supply function. So we set the two equations equal to each other. I want everything with Q on one side, everything without Q on the other side. So I'm going to add 150 to both sides, and then I'm going to add that e to the Q over 3 to both sides as well. That gives me 650 equals 2 e to the Q divided by 3. I divide both sides by 2, and I get 325 equals e to the Q divided by 3. To solve this equation, I'm going to take natural log of both sides. Taking the natural log of an e to the power, those are inverse operations, and they undo each other, and you're just left with the Q divided by 3. So Q is going to equal whatever 3 times natural log of 325 is. I put that into my calculator, and I got approximately 17.35. So that's my equilibrium quantity. And then to find my equilibrium price, I'm going to take this value and I'm going to plug it into either my demand equation or my supply equation. It doesn't matter which one. I'll plug it into the demand equation, and I got approximately 175. Okay, so to find the consumer surplus, I have to integrate from 0 to Q naught, my demand function, minus my equilibrium price. So in this case, I'm going to integrate from 0 to, I'm going to call it 17.4. I'm going to round just a little bit more, just to make the calculator part a little bit easier. So I'm integrating from 0 to 17.4. The demand function, which is 500 minus e to the Q divided by 3, minus my equilibrium price, which was 175. If I combine like terms, I get 325 minus e to the Q over 3. So to integrate, this is going to be 325Q minus 3 e to the Q over 3. And I will be evaluating that at 17.4, at 0, and subtracting. Where did that 3 e to the q over 3 come from? Q over 3 is the same thing as 1/3 times q. So this is like an e to the kx using my formula 1 divided by k. So 1 divided by 1/3. That's where the 3 came from. And then the e to the q over 3. I plugged in the bounds of integration, and I ended up getting approximately $4,667. Now, if we were asked to find the producer's surplus, we could do that as well. It's just a slightly different formula, but you would go through the same types of steps, and you would get a dollar value that gives you that producer's surplus. In this particular example, there's some symmetry, and you end up getting the same answer, but that doesn't always happen in every case. All right, so that was a lot of material in this lesson. As always, please let me know if you have any questions.